Alright, hello, this is Jeff Scott, and I've done several presentations talking about secure coding, including individual lessons on things like static code analysis, band APIs, and fuzz testing. But I'm going to go into a little bit more depth and breadth of coverage on fuzzing right now. This is a repeat of the lecture or talk, discussion, whatever you want to call it, that I'm giving at Data Dimensions on both Friday, the 13th of November, and Friday, the 6th of November. So let's just get to it. What I'll do first is just go over some terminology, and a lot of it I never mean to talk down to people, but just to make sure we're at a common focal point. We'll go in and get an informal definition of what fuzzing is and talk about the three major components of fuzzing, those being the poet, the courier, and the oracle. So, again, some of the stuff I'm saying in here I know is very general, very generic in nature, and you might think you know it already, and maybe you do. All right. As mentioned here, when software fails due to unexpected or malformed input, it's a robustness problem. All right. When it fails due to some type of deliberate attack, it's a security problem. That's what we've been talking about. If it causes harm or death, it's a safety problem. And really what you're trying to do when you're fuzzing is you're trying to make sure none of these happen, because all of these, all right, basically are introduced in the system through bugs. All right. And a bug is a mistake made by a developer. And let's face it, if developers make a million mistakes, 999,999 of them are accidental. That's just the way that it is. But as mentioned here, under the right conditions, the bug is triggered, which causes the software to do something it was not supposed to or not intended to do. So when you find and you fix bugs, you're going to generally, naturally improve robustness, security, and safety. As mentioned here, bugs are also known as code vulnerabilities, such as design vulnerabilities. Problems, things that were omitted purposely or accidentally in the design itself. Now this example here is a bit convoluted, but if you could imagine that we created some kind of a bank website that didn't require authentication. As mentioned on the bottom of this slide, design vulnerabilities are not under the purview of automated tools. In other words, they must be found and eradicated by humans. In much the same way, configuration vulnerabilities, where you've got a setup that exposes a vulnerability. The example given here, you've got a database and you never change any of the default settings or credentials. And it is amazing, there are still plenty of sites, etc. out there where the password, the login is admin and the password is admin. Again, these are the kind of bugs that must be found and eradicated by humans. All right. Then you've got code vulnerabilities, which are actually errors in the code. And these are found by humans and they're found by tools during a combination of both positive and negative testing. With positive testing, you're putting valid inputs into the software to make sure that it reacts correctly. So in other words, if you're asking for ages, like an age of a person, and maybe the range is 1 through 125, then what you're trying to make sure is that if you put in, that technically, that means that you've got 125 tests to run, if those are the actual valid ages. All right. As it says, these can be used to find and fix bugs related to functionality. If you find out something didn't work, if you've got an off by one error type of thing. On the other hand, fuzz testing is more of the negative type of testing. And that's where you send incorrect or often referred to as malformed inputs into software and you look for failure. All right, sometimes they're so malformed that any developer that's worth his or her salt will have written code that will have made sure that this didn't happen. For instance, if I ask for an age and I start to put in alphabetic characters, all right, I should have some kind of an is numeric type of check in there type of thing. As it says, this type of testing not only can be heavily automated, it normally is. And it normally is automated because with automated tools, you can oftentimes send millions, if not billions, of malformed inputs into a system and find out how the system reacts, where you could never do that by hand. You just wouldn't have the time or the person power to do that. All right, these different types of software vulnerabilities also go by 3 different names: unknown vulnerabilities, zero-day vulnerabilities, and known vulnerabilities. An unknown software vulnerability has not yet been discovered. All right, that doesn't mean it's not there. It is there, but it's there under the surface. And as we said, it hasn't yet been discovered. A zero-day vulnerability has been found, but it hasn't been published. So it could have been found. Ideally, it would be found by the company that created the software, so they can try to quickly fix it and publish a bug fix. But unfortunately, sometimes these are found by the bad guys, so to speak. All right? And you don't want them to publish it. When you've got a known vulnerability, it's been published. And ideally, either a patch or a fix has been created, has already been applied, or is on its way to being applied. All right, talk a little bit about black box testing. When you black box test, and much of fuzz testing that we'll get into in just a bit is black box testing. With black box testing, as mentioned here, the tool has no knowledge of the internals of the hardware. In other words, it doesn't really know anything about the software, and it doesn't have to. It interacts with a target or with a software solely via some kind of external interface. When you've got white box testing, that makes use of the target's source code. Typically, as mentioned, this type of testing uses static techniques. All right? And it could be even something as simple with a static technique. We've got here source code scanning, but really, when you think about it, it can be something that's as simple as manual code reviews. All right? All right. Then we've got gray box testing. Again, when we're talking about doing fuzz testing, it's either black box testing, where you don't know anything about the code or the source code, or gray box, which combines black and white testing techniques. As it says, the tools interact with the target via an external interface, as you have with black box testing, but it can also make use of the associated source code. All right, so as it says, fuzzing is an extremely useful tool, and actually it's the tool most often used by hackers to try to get into a system. As mentioned here, these types of vulnerabilities are found using both static and dynamic type of testing techniques. With static, as it says, it can be used without actually running the code. Source code reviews, but and the stuff that's mentioned here should be obvious to everyone. What are the problems with source code reviews? They're slow. They can be painstaking. It can be hard to get everyone together that has to be together. And you are basically, the success or failure depends upon the skill of the reviewers, the time of the reviewers, how they feel, the time of the day the review is held, etc. There are automated source code analysis tools. All right. And these, again, typically, a lot of times with these kinds of tools, they're good tools, but what they do is they give you examples of general types of problems that can and typically will be found. So they will produce reports, but as it says there, these reports, the information that becomes available from these reports still has to be reviewed by human beings. They're binary analysis tools. The advantage of binary analysis tools is if it's a third party, you don't have to give them access to your code, just a copy of the executable. All right. So let's get into dynamic testing. As it says, that's performed when the software is running. And here are 3 or 4 examples. The first is load testing. When you load test, what you're trying to do is put as much stress on the system as possible to see how the system will react to it. All right. So again, as it says, you want to see if it fails due to heavy volume. So if you know For example, that you've set your system up that let's say that maybe there's some kind of a software system that'll handle what maybe 300,000 people at a time, that kind of an idea. Well, then you test it with 100, then with 200, then with 300,000. But then you even go up and you test it more. You try to break the system. You want to make sure that the system, if it can be broken, that it degrades gracefully. All right, not that it just comes crashing to the ground. There's also interoperability testing. So you've got two implementations that speak a different language, but they're able to talk to one another. This is again a more and more important thing as time goes on, because you've got company A, and company A is a Microsoft shop, and they use ASP.NET for their applications, and they're talking with company B, and company B is a Linux or Starnix shop, and they use, I don't know, perhaps they use Java server pages to do their stuff. And then they talk with company C, or maybe they acquire company C. And that's an Apache shop. And they're working with PHP. So you got PHP, JSP, ASP.NET, 3 different types of APIs. All right? And they all must talk to one another. You've got conformance testing, where you've got some kind of specification, and you want to make sure that the tested system behaves the way that it should according to the specs, or conforms to the specs. Finally, again, fuzzing, and now we're going to get into it. Excuse me, we're going to get into it now in a little bit more depth and breadth of coverage. This is a very simple definition. It delivers malformed inputs into software to see if associated failures occur. So you're trying to break the system by giving it garbage input. Microsoft places fuzzing in its verification phase. Now, this is not a great slide. I actually took this with my phone, taking a picture off of an article that was on a PDF. But the point is, where we are in our discussions right now is we've gone through all the core security testing. We've talked about establishing security requirements. We've talked about bug bars. We've talked about security and privacy risk assessments. We've talked about its design requirements, attack surface analysis, attack surface reduction. We've had a whole lesson on threat modeling, and we went through an exercise on threat modeling. We've already talked about, just in the last few lectures, the approved tools from Microsoft, the deprecated unsafe functions. Where in this lesson, we've already been talking about static and binary, or dynamic, I should say static and dynamic analysis. Now we're into fuzz testing. All right, we've already talked a little bit about an attack surface review, and so we're basically getting toward the end here. Create an incident response plan, have a final security code review, certify, release, and archive, and execute your incident response plan. So again, the point is, as mentioned, we are talking about fuzz testing, which is in the verification, which is in phase 1, 2, 3, 4, 5 of 7 phases. Notice, as mentioned there, each malformed input that you put into a system is known as a test case. Every time you have a failure based on one of these test cases, you should actually look at it as a victory, just because of the fact you have now found a bug, and better that you find it during the testing phase than have you release it to a customer and have them find it when it's out in the, quote, real live world, unquote. Again, it's typically a black box technique, but it can be gray box also. And as it says there, the rules are off. There are no rules when you're talking about fuzz testing. Inputs are captured and used as a template. All right, there's 2 basic types here, and some books say what I'm about to say, and some books don't. And what I'm getting to is, I'm going to now talk about dumb fuzzing as opposed to smart fuzzing. Some books say there really is no such thing, there is no distinction, there is no blurred line there. But other books disagree, and I'm going to go by with what I found online with basically most of the Microsoft stuff. And with dumb fuzzing, what you're doing is you're giving random input data. Since most of the input is invalid, You can get a lot of input, but you're probably going to find very few cases that are reminiscent of what you're actually looking for. So in other words, you would expect that most of these random tests would just fail automatically right away. That's why it says here, it takes a long time to enumerate valid test cases. All right. With smart fuzzing, then you know about the associated code. So you do things like replace null terminated strings, alter numeric values or flip signs. If you're working with bits, make zeros ones and ones zeros, etc. Add, duplicate, or alter header information. We've talked about that a little bit in an earlier lecture. All right. A complete fuzzer then has three different components. It has what's called a poet. It has a courier, and it has an oracle. You can see they go by other names as well. With the poet, it creates your malformed inputs or test cases. Notice an effective poet must be smart enough to craft test cases that are most likely to trigger bugs. In other words, a good poet, what it will do is it will come up with test cases that are close to valid input, but that are not valid input. So as it says, close to what the target expects, but malformed in some way. There's 4 different types of poets. The first one I mentioned to you already was the random poet. All right. Usually, again, this is the simplest to create. There was an article I was reading on the simplest dumb fuzz random poet, and it was like 5 lines long, written in Python. But since it's the simplest, it also is the least effective. And as it says there, it's because of what I mentioned before, because most of the test cases do not actually resemble valid input. Then there's a template poet. As it says, it introduces mostly correct anomalous inputs for test cases. And I really should change that to not anomaly input, but anomalous. All right. As it says, these are good, they're fast, you can get them up and running quickly, they're normally adjustable, but there are usually not a lot of good templates that are out there. So you might have to write one by scratch. There's a generational poet. Notice what it says. It understands everything about the protocol, file format, or API it's testing. So as mentioned there, it knows all the rules. So it can choose to systematically follow, bend, or break these rules. A generational poet, as mentioned right here, creates high-quality test material that looks legitimate to the target software. Finally, you've got an evolutionary poet. And when you think about evolutionary, think about the fact that it grows as it runs. So the idea with this is that it uses feedback from previous tests to evaluate the behavior of the target. And then it can adjust its tests accordingly to make them more and more reminiscent and make them closer and closer to actual valid type of inputs. All right, so that was the poet. Next we have the courier. And as mentioned here, the courier delivers the best test cases created by the poet to the target software. And there's 4 types. There's network protocol fuzzing. As it says here, this code interprets protocol messages because they're a potential attack vector. So fuzzing can be used here to locate known vulnerabilities. There's file fuzzing, all right, where malformed files are delivered to a piece of software. The best method, as it says right there, is to often write your own custom wrappers to facilitate feeding test cases to the target. So this will take some work typically on the developer's part. You've got API fuzzing. Because you want to see how the API itself reacts to malformed input. And finally, you've got UI or user input fuzzing. And when you start to think about the way that all this stuff is set up today, again, I was reading an article on this, and they mentioned that there was an app, and on the screen, The idea was it was a touch screen application that a place had created. And you had to like do 2 quick taps on the left-hand side of the keyboard. So when they started to do UI fuzzing, they started tapping the right side of the keyboard or tapping the left and the right side simultaneously just to see what would happen as this was being done. All right, so we've talked about the poet, we've talked about the courier, and now it's time to talk about the oracle. As mentioned here, the oracle detects whether or not failure has occurred in the target. In other words, did your test case pass or fail? If it fails, typically the system either crashes, goes into an infinite loop, experiences some kind of resource leak or shortage, or has some other kind of unexpected behavior. Now, when you look at this, as mentioned right here, these are traditional methods that you can use, or traditional types of oracles. And the best is still humans. It says eyeballing there, but it's human observation. As mentioned here, especially for test setup and initial testing, this is often the most used technique. Valid case oracles. Checks the health of the target by sending it valid input and looking not only for a valid response, but for a timely one as well. Typically with these, as mentioned here, they're simple, they're easily automatable, they're black box, and they're typically focused. Resource monitoring. As it says, what you're looking for is, did you run out of memory? Was there a memory leak? Was there a problem with the CPU? What was it? What did any kind of resource happen that was out of the ordinary? Any kind of resource problem. And external problems. As mentioned here, it is not possible to make a generalized oracle that works for everything and everyone. Dynamic binary oracles. All right. With dynamic binary, again, the idea is you have the executable. You don't have the code itself. There are a lot of third-party vendors now that literally will take your executable and they'll run fuzz tests on your executable. And you don't need to give them your, quote, real code. Now, that doesn't mean if you give them the executable, I guess, probably if they wanted to, they could try to reverse engineer it and get your real code. And there's plenty of tools that exist that allow you to do this. All right, source code instrumentation. Again, as mentioned, if the source code is available, there's other things that you can use, like running it into a specialized debugger. All right, compiling with special debug symbols and tools. Using special software that exposes memory usage errors. And there can be other things available as well. Functional and behavior checks, as mentioned here, certain attack vectors can be examined to detect function failures. So to summarize, and I found this interesting, you may or may not, but fuzz testing was actually developed by a professor, Barton Miller, working at the University of Wisconsin-Madison in 1989, which makes it, if my math is right, between 16 and 17 years old. As mentioned there, his work continues today, and a lot of the work he did along with his students. So today we've talked about fuzz testing. And as mentioned, the basic idea is to intentionally deliver malformed input into target software to try to detect failures. A couple of the things, the advantages of fuzzing, as it says, requires least effort in finding bugs. It's verifiable. It should be reproducible. Should be scalable. Disadvantages can be costly. All right. Increasing coverage increases runtime. You may miss bugs. All right. You may think that you've got everything handled, and you find out that you don't. We saw that a fuzzer has 3 different components. The poet that creates the malformed inputs, also known as test cases, the courier, which delivers the test cases to the target software, and the oracle, which detects the target failures. Fuzzing should be used by everyone, both the company that creates the software and the company that uses the software, if and when possible. As mentioned previously, fuzzing is an integral part of the Microsoft SDL. As mentioned before, it's in the verification phase. And I want to leave you with this. All right? I took this picture about a week ago at Blackhawk Technical College, and as I'm doing this lecture right now, it is Thursday, November 12th, and yesterday was Veterans Day. And what I mentioned was, and I know that there are a lot of people who work at Data Dimensions who are veterans, and I said, I'm not a veteran, but I appreciate all the work that our veterans have done, etc., in all of their service. But what I said last week, and I think that everybody, the veterans who were in the crowd, understood this, but I said this, and I prefaced it by saying I was not trying to be confrontational or offensive. But to me, to have any kind of day like a Veterans Day, in some ways, to me, is kind of condescending, because you should be celebrating veterans every day, all right, not just one day. But I said, I don't know if there's a certain number of these flags. I think they actually go all the way around the circle here by the flagpole. But somebody asked if there was significant, if there was a number. I said, I don't think so. But I said, why do you think those flags were there? And, right away almost somebody said, well, it's just about Veterans Day, I suppose, to commemorate Veterans Day. And I said, yeah, it's to raise awareness. And again, that's what I'm doing in these training sessions. I'm attempting to raise awareness. All right? So remember, today we talked about fuzz testing. And what I am going to talk about in the next couple lectures, because I'll have 2 more of these presentations, the next one I'm planning at least on it being on a combination of cross-site scripting and SQL injection, and then the last one will be on buffer overflows. Okay? Thank you for listening.